So now let's talk about a little bit more kinetic theory. And what I want to use is that familiar Haber process that we've seen so much in thermodynamics and equilibrium. So we're going to take 3 moles of H2 gas and 1 mole of N2 gas. And we will obtain 2 moles of NH3 gas. Now, in terms of kinetics, I can describe this reaction experimentally by measuring the rate of disappearance of a reactant or the rate of appearance of a product. And we have to account for the stoichiometry when we do it this way. The rate of the reaction would be equal to minus 1/3 the change in H2 concentration over the change in time, which would also be equal to minus the change in N2 concentration over the change in time, which is equal to plus 1/2 the change in NH3 concentration over the change in time. So that is our way of accounting for the stoichiometry of this reaction. We also can look at, so this is more of a derivative, if you will. So let's look at a simpler process where I'm simply converting A to B. The rate of the reaction is equal to the negative derivative of A with respect to time. Now that's really the more sophisticated mathematical form of delta A over delta T. If we find out that this disappearance is first order, that also means that the reaction rate is minus K concentration of A to the first power. Actually, it should be plus K to the first power. When two variables are equal to the same thing, I can set them equal to each other. That means minus dA over dt is equal to Ka. Now I can do a little bit of integral calculus here. I wouldn't get hung up on the calculus itself. I simply want to show you how we get this integrated rate law. It's the result that ultimately matters here, but I can rearrange these variables and I can get dA over A is equal to minus K dt. And I can integrate this over the interval of the initial concentration to the final concentration. And on the other side of the equation, from time equals 0 to time equals t. And when I integrate this, I will get the natural log of A minus the natural log of A naught equals minus KT. Now I can do a little bit more math with this. the log of A is equal to minus KT plus the log of A naught. That is in the form y equals mx plus b. Meaning that if I were to graph a first order process, we'll have more to say about this later, and I graph the natural log of the concentration as a function of time, I will get a straight line with a constant negative slope. And that, if I take the negative of this slope, I will have the rate constant of the reaction. So this is one way that I can manipulate variables and determine if it's first order or second order or zeroth order, etc. Now let's talk about something a little bit more interesting and practical, and this is something you'll especially see on standardized exams. Let's take a look at the reaction at the bottom third of this page. I have 2NO plus O2, which yields 2NO2. NO, those are gases, plus O2, which of course is a gas, and I yield 2NO2. If I wanted to analyze the kinetics of this reaction, and this is something that we can do lots of different ways. When everything is a gas, a really clever way of tracking this reaction is to look at changes in pressure. Sometimes you'll have a colorimetric reaction where a color change will occur. Certainly, some kinetics reactions are easier to monitor than others. As long as there's a change in the number of moles of gas, pressure is a pretty good one to do. So if we go back and look at this data, we have 3 experiments. Notice we only care about the initial concentration of the reactants and products. That's for a very specific reason. They will always be greatest in the beginning, and the decrease is greatest at the beginning. So you want to, it's easier to measure these changes if you measure the change at the very beginning of the reaction. So what I want to do here is to simply copy this data onto the easel, and then I'm going to show you how we manipulate it. So here we have our data, and what you really want to do is first write what we call an implicit rate law. That means that the rate of the reaction, V, is equal to the rate constant. Now this is a lowercase k, not to be confused with an uppercase K that is the equilibrium constant. The rate constant will come with units, whereas the equilibrium constant is unitless. Times the concentration of NO. But here's the deal. I do not know what the exponent is because I do not know if this reaction occurs in one step or more than one step. Times the concentration of O2 to yet another power. Now, X and Y could be the same. They could be different. They could be non-integers, but they probably won't be on anything that you would see on an exam. So here is how we find the values of x and y. We are temporarily going to ignore the value k because it is a constant. We want to look at two experiments where one of the reactant concentrations does not change. So if I look at experiment 1 and 2, the concentration of NO doesn't change. If I take 0.12 and divide it by 0.12, I get 1. And 1 to any power is going to be 1 and effectively drops out of the problem. O2 doubles as I go from 1 to 2. So that will be 2 to the y. What happens to the rate? It also doubles. 2 to the y equals 2 to the 1. This way the bases cancel out neatly. And y is equal to 1. I'm going to box that, and we'll come back to that in a moment. Now, let's look where O2 doesn't change between experiment 1 and experiment 3. NO doubles, which will be 2 to the x. 0.05 divided by 0.05 is 1. 1 to the y, which we now know is 1, is going to be 1, so it effectively drops out. 2 to the x equals, notice this goes up by a factor of 4, which is 2 to the 2. The bases neatly cancel. And now I'm left with a value of x equals 2. Next, I can write the explicit rate law now that I know the values of x and y. V equals the concentration of NO to the 2 times the concentration of O2 to the 1. We say that V is second order with respect to NO. That means in the slow step of the reaction, there are 2 molecules of NO. So the slow step is what determines how fast the reaction will go. There are 2 NOs. And there is 1 O2. If we go back and look at the stoichiometry of the reaction, there are 2 NOs and only 1 O2. This is excellent evidence that this reaction occurs in one step. Now I also need to find the value of my rate constant. I can pick any one experiment that I want. I can pick experiment 1 or experiment 2 or experiment 3. I'm going to pick experiment 2 at random. I'm going to plug in these values and then I'll solve for the rate constant. Now these units are molar and molar and molar per second. So solving for K, K is equal to V divided by the concentration of NO to the second power times the concentration of O2. That is 0.24 molar per second divided by, I could do 0.12 squared, but if I'm on a test that doesn't allow a calculator, I would prefer to do it this way. And I think it'll be obvious in a moment. Times 0.1, and that's going to be molarity to the third power. Meaning that this molar cancels and this becomes a 2. So my unit is going to be molar to the minus 2 seconds to the minus 1. Now, 0.24 divided by 0.12 is 2. 2 divided by 0.1 is going to be 20. So this is going to be 20 divided by 0.12. This is 200 divided by 1.2, which is 200 divided by 6 over 5, which is the same as 200 times 5 divided by 6, which is 100 times 5 divided by 3. That's 500 divided by 3. That is 167. And now I have my value for K. So now I plug this into this equation. I have my final rate constant. V equals 167 molar to the minus 2 seconds to the minus 1 times the concentration of NO squared times the concentration of O2. Meaning if I know my concentrations at any point, I can determine what the velocity of the reaction is. This is called the explicit rate law. No more assumptions. We've got all the raw math. So going through this process and having data and being able to start with an implicit rate law and convert it to an explicit rate law will be very important.